Okay, so this is chapter 4, which is the final chapter for linear algebra. Okay, so eigenvalues and vector is a very short chapter. Okay, so the first one is we will cover eigenvalues and eigenvectors, what it means by eigenvalue and eigenvectors, and also how to find them. Mainly calculation, not quite difficult. Okay, their step is quite easy actually. The second part is the diagonalization and similar matrix. Here we will talk about how to diagonalize a matrix. Okay, so the first one is the eigenvalues and eigenvectors. Okay, so here is the definition of eigenvalue problem. Okay, so if we have a square matrix, and then x is the column vector, and then lambda is a scalar. Okay, then any problem in this form, ax equals to lambda x, this is called an eigenvalue problem. Okay, so here lambda is the eigenvalue of a, and then x is the corresponding eigenvector of a associated with lambda. Okay, so next is how do we find the eigenvalues and eigenvectors. So there are two steps here. Okay, so the first one is you need to determine the roots of the characteristic equation. So what is the characteristic equation? This is the formula. So it's the determinant of A minus lambda I. So I here is the identity matrix. Lambda is what we want to find. A is the matrix. This is given, and then equals to 0. So the root lambda here is the eigenvalues. Okay. Once we have the eigenvalue, so for each eigenvalue lambda, so we need to find all the non-trivial solutions to the homogeneous system a minus lambda I x equals to 0. So this is a linear system, a homogeneous linear system. So then for each lambda, we will find an eigenvector. Okay. So this is what you need to remember, the formula and this. Okay. Okay, so for example here, you are given a matrix A, compute the eigenvalues and the associated eigenvectors of the matrix. So the characteristic equation, so the formula is this, determinant A minus lambda I. Okay, so A is this matrix, and then minus lambda I. So if you multiply, simplify, you will get this. Basically, it's just 1 minus lambda, and then negative lambda, 5 minus lambda. So all these terms, we have lambda because of this I. I is the identity matrix. So meaning if you write the characteristic equation in full before getting this is basically is this determinant A minus lambda I. So this is matrix A. So this is matrix A minus lambda I. I is this. So basically this part is actually is equals to minus lambda. Is lambda 0. Okay, so if you do subtraction, you will get this. Okay. So equals to 0. So basically here you use the cofactor expansion to find the determinant. So if you simplify, you will get this. But normally in the process of getting this, we will do the factorization. Uh, we do the factorization at the same time. Okay. So for example, here I'll just show one example. Basically, this example how we get to this point without getting to this. Okay. So we know that we have from the characteristic equation, we will obtain this. Okay, so this is what we get from the characteristic equation. So then, let's say we do cofactor expansion along row 1. Okay, then we will have, so remember the plus minus sign, plus minus sign. So you have a 1. So you have 1 minus lambda. Okay, so this is the first term, and then minus 2. So you have 1, 4, 1, 5 minus lambda, and then minus 1 here, plus minus is minus 1. So you have 1 minus lambda. Okay, then you just simplify everything. So here you have minus lambda, 5 minus lambda, plus 4, minus 2. So from here, if you multiply, you get 5 minus lambda, minus 4, then minus 4 plus 4 lambda. So don't be so eager to expand this. We try to simplify everything in the bracket first. Okay, so 1 minus lambda. So if you simplify this, you will get lambda square minus 5 lambda plus 4. Then minus 2. This is 5 minus 4 is 1. Then minus lambda plus 1. Then plus factorize 4 from here. You have because here is a minus here, so you factorize minus 4. So then you have a 1 minus lambda here. Okay. So if you can see, there's a similar factor here, common factor, 1 minus lambda, 1 minus lambda, 1 minus lambda. So factorize 1 minus lambda, and then keep the rest in the bracket. Plus 4, then minus 2, plus 4. Here you get this lambda square minus 5 lambda plus 6. Okay, equals to 0. Then from here, you can factorize because it is a quadratic equation. So you have lambda, lambda 3, 2, so minus, minus, okay. So then this is, again, this is the same as the previous one. It's the same as the previous one. Okay, here. That's the previous one. Okay. Now, let's say if you choose the different, just now we choose this row to do expansion. Let's say you do another row to do the expansion, but and then you cannot do the factorization, and at the end you obtain this. So how do we get from here to this? You know how to do the lone division? Do you know how to do the lone division or not? Still remember? Yes, sir. Okay. Then from there you just do lone division. So I will not show you how to do lone division unless you need me to show you. So for the chat box, you say you still remember, so no need lah. Okay. Okay. So next is this. Okay. So from here, we get 3 lambda. So lambda equals to 1, 2, and 3. So from here, we have 3 lambda. So meaning for this matrix, we have 3 eigenvalues. First is 1, the second is 2, third is 3. So for each eigenvalues, we need to find eigenvector. Okay. So how do we find eigenvector? Find eigenvector. So it's basically is here. So once we have the eigenvalues, so you need to substitute each lambda to this system. Remember the second step? The second step, this is the second step. You need to solve this system. Okay, a minus lambda I x equals to 0. So that's why we have this system here. So because we have 3 lambda, so we label it as lambda 1, lambda 2, lambda 3. So meaning for lambda 1, we have x1 here. There's a typo here. This one should be bold. Bold x1 is a vector. It's a matrix. It should be bold. Do not confuse this with this. Okay, this is, so in writing you should write like this. Okay, bold is a matrix, and then this is constant. This is one unknown only. Okay. So from here you substitute lambda equals to 1. Okay, lambda equals to 1 into the system. So just now remember we have 1 minus lambda and then negative lambda, 5 minus lambda. So now what you do is you substitute lambda equals to 1. Substitute lambda equals to 1. Lambda equals to 1. And then you simplify. So 1 minus 1, you get 0. And then this is minus lambda, so minus 1. 5 minus 1 is 4. Okay, the rest is the same. So after that, we have this system. It's a linear system. So you just use the Gaussian elimination. You can use the Gauss-Jordan method to solve the system. Okay, so let's say I use Gaussian elimination. Okay, so we reduce the matrix into REF form. So that one will not show here because we covered that already. You go back, you verify whether we get this or not. Okay, so if you apply the Gaussian elimination, so we will get the augmented matrix in REF form, in this form. Okay, so remember here we have a x1, x2, x3. Okay, so from here, from the second row, we know that x2 minus x3 half equals to 0. And then we do not know what is x3, so we label x3 equals to r. Okay, and then any real number, then from here you can get x2. So x2 equals to r over 2. So that's why we have this. And then from the first row, you can get the first one. So remember, this is a vector x1. Okay. Boleh? Now, once you have this, because one eigenvalue, we have an eigenvector. Eigenvector must be in value form. It cannot be in R form. We don't want that in R form. So what we do is we take R equals to 2, but in fact R can be any value. But why we choose R equals to 2? Because there's a fraction 2 here, okay, over 2. We want to get rid of fraction, okay, because we prefer whole number. We don't want fraction. So that's why we choose R equals to 2. So if you choose R equals to 2, then the eigenvector equals to -1, 1, 2. Okay, so this is the eigenvector for the eigenvalue lambda 1 equals to 1. Okay, now let's say you insist you don't want to choose R equals to 2. That's fine. You want to choose R equals to 1 is also can. So then your eigenvector will be in different form. So your eigenvector will be 1 over 2, 1 over 2, 1 here. Okay, it's up to you. Yes, Rahul, you want to ask question?
So, sir, the eigenvalue, we can set the value as long as it's not a trivial value, is it?
Eigenvalue is what we obtain, not you set.
Ah, okay.
It is we obtain from here.
The calculation, and after that we
Yeah,
use
from here.
equal to something, right? Okay.
It's from here. So from here you get lambda equals to 1, 2, 3. So what we do is because there are 3 lambda, so you do labeling lambda 1 equals to 1, lambda 2 equals to 2, lambda 3 equals to 3. Then you substitute each lambda to this system to find eigenvector x. Okay. So for the first lambda, lambda 1 equals to 1, we have this. We have this eigenvector. So we do the same thing for the second eigenvalue. Okay, lambda equals to 2. Okay, so we substitute into here. So again, this is the original equation. A minus lambda I. This is A minus lambda I. And then this is again, there's a typo. Okay, it's a ball. This should be x2 ball equals to 0. Then you substitute lambda equals to 2 because now lambda equals to 2. So you substitute lambda equals to 2 here. So you have this. Simplify again, we get this. Again, you need to do the same thing. Use Gaussian elimination, reduce it into RDF. and then you solve it. This is the eigenvector in general form. Okay. Again, we need to choose R, so the eigenvector is in the value form, not in general form. So since we have a fraction denominator over 4 here, so we choose R equals to 4. Okay. So, but again, R can be any value. So if you choose R equals to 4, then our eigenvector is this one. Okay. So this is the eigenvector for this eigenvalue. Okay. So you need to remember for each eigenvalue, you have a different eigenvector. Okay. Okay. For the third eigenvalue, lambda 3 equals to 3. So you substitute lambda equals to 3 in our system here. Again, so this is a matrix. Okay, it's a bold here. You need to repeat the same thing, but now lambda equals to 3. Okay, so you have this. And then you simplify, again simplify. And then you have in REF form. Similarly, you get this solution. So this is the eigenvector. Again, there's a denominator 4 here. So we choose R equals to 4. So then we get rid of the denominator. Then you have this. So this is the eigenvector for the lambda equals to 3. Now another way for us to do this, if you don't know what R to choose, let's say you do not know, and you don't care about your eigenvector here, meaning fraction is okay for you, what you do is from here you factorize R. Okay, so from here you can factorize R out. So factorize R, you have minus 1 over 4, 1 over 4, 1. And then this is your eigenvector, this part. Okay, if you don't know what R to choose, this is another way for you to find eigenvector. Now, any questions so far? I think this is a new thing for you. Boleh ya?
All right, sir.
What about the negative sign? Where is the negative sign? You mean here? The negative sign here? Is it? Oh, negative sign you can cancel out. Boleh? Yeah. Okay, we go to the second example for the eigenvalues and eigenvectors. Now this is a little bit complicated, okay, because involving surd, but not complex number, it's just surd. Okay, so we are given a new matrix. Find the eigenvalues and eigenvectors. So same thing, the first thing is you need to find the characteristic equation. So this is the formula for the characteristic equation. So basically in this form. Now, here if you do the cofactor expansion, at the end you will get this. Okay, 2 minus lambda bracket multiply lambda squared minus 4 lambda plus 2 equals to 0. Now, this part you cannot factorize just by trial and error. What you do is you need to use the quadratic formula. So you to find the factor. You remember what is the formula to find this factor?
The negative b plus minus b square minus 4ac.
Yes, correct. Negative b plus minus, uh, what is it already? B square.
Square root.
B square minus 4ac over 2a. Okay. So lambda equals to this. So for this part, you need to apply the formula. So if you apply the formula, you will get 2 plus Z2, 2 minus Z2. So from here, you get lambda equals to 2. So again, for this matrix, we have 3 lambda, 3 eigenvalues, lambda 1, lambda 2, lambda 3. So for each lambda, you need to find the eigenvector. Okay, so first, for the first eigenvalue, lambda equals to 2. So you substitute lambda equals to 2 into our homogeneous system. Okay, so substitute here, you will get this. Simplify, you will get this matrix. And then use Gaussian elimination, you will obtain this. Okay, so from here, this is the unknown x1, x2, x3. So from here, x2 equals to 0. So that's why you have 0 here. And then from here, you have x1 plus x3 equals to 0. So you let, here is either you let x3 equals to r, or you let x1 equals to r. It doesn't matter. So the solution here, I think what they did is let x3 equals to r. Okay. No, it's let x1 equals to r. Sorry. It's let x1 equals to r. So r, any real number, then x3 equals to negative x1, so equals to negative r. So that's why we have this. Okay. So again, you either pick any value for r. So here there is no fraction involving, so normally we just choose r equals to 1. So you will have this. Okay. So this is the eigenvector, okay, eigenvector for the first lambda. Okay, next you do the same thing for the second eigenvalue, okay, 2 plus Z2. Now because there is a Z2 here, it makes our calculation a little bit complicated. So you just substitute lambda equals to 2 plus Z2. Simplify, you will get this. Okay. And then you solve it using Gaussian elimination. Then you will obtain our eigenvector will be like this. And then again you choose lambda r equals to 1. Okay, then you have our eigenvector equals to this. Okay, so this is the eigenvector for this eigenvalue. You do the same thing for the third one, 2 minus Z2. Okay, so substitute that into our system. And then you solve it using Gaussian elimination. And you will get similar eigenvector. Again, you take r equals to 1. So this is the eigenvector for this eigenvalue. Okay? Any question so far? Molly? It's just calculation only. The process is the same. As long as you remember the step, there are 2 steps. You remember the step is quite easy lah. Unless you don't know how to do the Gaussian elimination, the Gauss-Jordan. If you master that, this is a piece of cake for you. Okay, next, the properties of the eigenvalues and eigenvectors. Okay. Now for any square matrix, if you do sum of eigenvalues, so this is actually equals to the sum of the diagonal terms of A, and this is called the trace of A. The notation is TR bracket A. So in formula, this is how we write. Trace A equals to the summation lambda I. So I equals to 1 to n. Okay. So you just remember, if you do summation, if you add all the eigenvalues together, this is called the trace of A. Next is the product. If you do multiplication of all the eigenvalues, multiply. So this is the symbol for product. Product. Okay. So meaning multiplication for lambda I. So if you do that, this is actually equals to the determinant of the matrix A. Okay. So meaning if you know the eigenvalues for a matrix, then you can find the determinant by the multiplying the eigenvalues. Don't need use the cofactor expansion, just the one we learned in chapter 3. You just multiply the eigenvalues. Now the third one is the linear independent of eigenvectors. Linear independent, I think this is the new concept for you. So what does it mean by linear independent? Okay, eigenvectors of a matrix A corresponding to distinct eigenvalue. Distinct means different. To distinct eigenvalues are linearly independent. So this is a statement, is a fact that you need to accept, that eigenvalues for a matrix A corresponding to distinct eigenvalues are linearly independent. What does it mean by linearly independent? It means one eigenvector cannot be written as a linear sum of other vectors. Okay, so what does it mean by that? So we go to see this example. This is what we obtained in the previous example. You have three eigenvector x1. Again, there's a, it should be bold here. Should be bold here. This should be a vector. Okay. Linear independent, there are two things that you need to check. Okay, one thing is that you see clearly none of these eigenvector is a constant multiple of any other. What does it mean by constant multiple? Meaning you cannot obtain x2 from something times x1 is a constant multiple. Nor is any one obtainable as a linear combination of other two. So what does it mean by this? I will explain. The first one, constant multiple. I think I show you one example where this is a constant multiple. It's easier for you to understand. Okay, let's say x1 is 1, 1, 1. Is the easiest one. X2 is 2, 2, 2. Now you can, from here you can know straight away that x2 is actually 2 times 1, 1, 1. This is 2 times x1. So this is a constant multiple of any other. So if you have this case, then this is not linearly independent. Okay, that's the first case. So far boleh? The second explanation is that linear combination of any two. What does it mean by linear combination? I think you don't remember anymore. It's already covered in, I can't remember, chapter 1 or chapter 2. You go back, you refer to your slide. Now I'll show you one example. Let's say x1 is 1, 0, 1. This is one eigenvector. And then another eigenvector is 0, 1, 0. and then another eigenvector is 1, 1, 1. Okay, so linear combination means from these three eigenvectors, x3 is actually x1 plus x2, correct? If you have this case, then this is called linear combination. Okay, then if you have this case, this is not linearly independent. This is not linearly linearly independent. Linearly independent. It's difficult to write here. It's not linearly independent. Okay, it's not linearly dependent. Okay, faham? Linearly independent is very important for the coming topic. So far boleh? Boleh. Now, that is the third property. Now, the fourth property is the eigenvalues of a diagonal matrix. Okay, for any diagonal matrix like this, the eigenvalues are simply the diagonal element. So, meaning for this diagonal matrix, the eigenvalue are A, B, and C. No need to do anything, you just straight away mention that for this matrix, the eigenvalues are A, B, and C. No need find characteristic equation. Okay? So that's the property. Now next is the diagonalization of a matrix. Okay, so basically what it means by diagonalization is that you transform a non-diagonal matrix into an equivalent matrix which is diagonal and simpler to deal with. The first case, we consider the case where we have a distinct eigenvalue, meaning different eigenvalues. It's not repeating, it's not the same. So this is the statement that we discussed just now. A matrix A with distinct eigenvalue has eigenvectors which are linearly independent. So this is a fact. You need to accept it. Okay. So if you form a matrix P, whose column are these eigenvectors, it can be shown that determinant of P is not equal to 0. Then the inverse exists. So the product of inverse matrix P times A times P is a diagonal matrix D where the diagonal element are the eigenvalues of A. Okay, so meaning for any matrix A, if you have a distinct eigenvalues lambda 1, lambda 2, lambda n, and then with the eigenvectors x1, x2 until xn, okay, again this is a vector, then the matrix P is formed by you just combine the eigenvector x1, x2. So this is the first column, second column, third column until n column, and then we'll produce a product like this, where this is the first eigenvalue, second eigenvalue, third eigenvalue, and so on. Okay, so this is the eigenvalue for this eigenvector, this is the eigenvalue for this eigenvector, and so on. If you swap the order, x1 and x2, if you swap the order, let's say you put x2, x1, and so on, then the lambda here also needs to swap. Okay, the position is according to the eigenvector. Now here the matrix P is called the modal matrix of A. Okay, and then since D is a diagonal matrix where the eigenvalues are the same as those of A, then the matrices D and A are called similar. Okay, And then the transformation, this transformation is called the similarity transformation. So these are the few things that you need to remember. The modal matrix of A is a matrix P, and then this is the similarity transformation. And then there's a typo here. This is a PDP inverse. Okay, so you can also find A from here because you have this transformation. If you do the other way around, you will get matrix A from this formula. Okay. Now example here. Let A is this matrix with eigenvalues -1 and 5, and the eigenvectors is this and this. Obtain the matrix model matrix P and the product this. Now this is actually the D, okay, the diagonal matrix. Now the model matrix P, how you get model matrix P is you combine the eigenvector. Okay, so there are two ways because there are two eigenvector here. First one is you put this in the first column and then this is the second column. So if you put this in the first column, then for this matrix, it will be this, the corresponding eigenvalue first, and then 5 as the second eigenvalue for the second column. Now alternatively, if you swap the order of the matrix P, then your D is also need to be swapped. Okay, so that's how we get model matrix and the diagonal matrix D if you have the eigenvalues and eigenvector. Now another question is let A be this. Can A be diagonalized? Okay. Now the eigenvalues, if you do find the eigenvalue, so the eigenvalue is equals to 1 and 1. So this one you can verify at your own. I will not show here. And then, so if you find the eigenvectors, then it will meaning for lambda equals to 1, if you substitute lambda equals to 1 into the homogeneous system, you will get x2 equals to 0, and then x1 you don't know, so then you just assume x1 equals to r. So our solution will be in this form, r0. Okay, so if you can rewrite this one is actually r times 1, 0. So this is the eigenvector. Okay, so meaning the eigenvector here is a multiple of this, because we need to have a 2 eigenvector, and then here only got 1. So since A does not have 2 linearly independent eigenvectors, so it cannot be diagonalized. Okay, so meaning if you have 2 eigenvalues, you must have 2 linearly independent eigenvectors in order to be diagonalized. Otherwise, it is not diagonalizable. So that's why we will have another theory here is or another point here, where the diagonalization of a matrix with repeated eigenvalues like this, lambda equals to 1 is repeated 2 times. Okay. Now, the first statement, if you look at the first statement, if the roots of the characteristic polynomial are distinct, meaning the eigenvalue are distinct here is all different from each other, then A is diagonalizable. So there is no question for a distinct eigenvalues. Now the problem comes when the roots are not all distinct. Okay, and A may or may not be diagonalizable. Okay, So how do we make sure whether A can be diagonalizable or not? It depends on this. A square matrix with repeated eigenvalues can be diagonalized provided we can obtain a linearly independent eigenvectors for it. So meaning for each case, for each repeated eigenvalues of multiplicity n1 greater than 1, we can obtain m linearly independent eigenvectors. Now, for example here, to be clear, for example here in the previous example, lambda equals to 1 is an eigenvalue of multiplicity 2. For previous example, multiplicity 2, because repeated 2 times 2, multiplicity 2. So then the matrix can be diagonalized if and only if we can find two linearly independent eigenvectors associated to lambda equals to 1. If you can, then it is diagonalizable. If you cannot, then it is not diagonalizable. Okay? So it can be shown that if lambda is an eigenvalue of A of multiplicity k, we can never find more than k linearly independent eigenvector associated with lambda. Okay? So for a repeated eigenvalues, I just make conclusion. So for a repeated eigenvalues, if the eigenvalue is repeated m times, if you can find m linearly independent eigenvectors, then it is diagonalizable. Otherwise, it is not diagonalizable. Okay? We will go to the example to see which is diagonalizable, which one is not diagonalizable, so that it is clearer for you. Now, let A is this matrix. Can A be diagonalized? Okay, so first you need to find the eigenvalues. So this is the characteristic equation or characteristic polynomial. Sometimes we use characteristic polynomial, sometimes we say it's characteristic equation. So you will get this. So if you do the determinant, find the determinant using cofactor expansion from this matrix. For this matrix, it will be easier if you choose row 1 because we have 2 0 here. So that's why you have a lambda, negative lambda, because plus minus plus, okay, negative lambda. Delete this, multiply this, you will get 1 minus lambda squared. So from here, we have 3 eigenvalues. The first one equals to 0. Remember, we have equals to 0 here. So first lambda is equals to 0. Second and third lambda comes from here. Even though it is square, it means lambda 2 equals to 1, lambda 3 equals to 1. Because in full, this is actually 1 minus lambda, 1 minus lambda. Okay. So then you can see that lambda equals to 1 is multiplicity 2. It repeated 2 times. So if you are able to find two linearly independent eigenvector for this eigenvalue, then A can be diagonalized. Otherwise, no. So we have to find. So substitute lambda equals to 1 into the homogeneous system. So you will get this. Now from here, basically, from row 1 and row 3, we will get that x1 equals to 0. Okay, so this is column for x1, x2, x3. So from these two equations, from these two rows, we will only get x1 equals to 0. But x2, we don't know, x3, we don't know. Okay, so that's why we have R and S. So the eigenvalues, we can choose any values for R and S. Now, sometimes it is quite difficult for you to choose which R and S so that we have two linearly independent eigenvalues. One way is you factorize from here. Okay, so meaning if you factorize this, if okay, so this one equals to, if you factorize this factorize this by R and S. So the first, if you factorize R, okay, then you will get 0, 1, 0. And then for S, you will get 0, 0, 1. So if you do factorization, then you will straight away you will get two linearly independent eigenvectors. Okay, so then we have two linearly independent eigenvectors for lambda equals to 1. Okay, and then for the third eigenvalue, lambda equals to 0, you do the same thing, substitute into the homogeneous system, and then you solve it, you will get this. Again, if you choose R equals to 1, okay, choose R equals to 1, so you will get our eigenvector is 1, 0, negative 1. So if you compare this eigenvector and these eigenvectors, these trees are linearly independent. Okay, so therefore A can be diagonalized. Any questions so far?
No, sir.
No one? Now, another example. Another example is this. We have a similar matrix A. Again, can A be diagonalized? Now, if you do the characteristic equation, we will obtain the same eigenvalue lambda. Okay, so from here we choose column 1 if we do the cofactor expansion. So this is a plus, minus, plus, so you get negative lambda. So if you delete this, you will get 1 minus lambda, 1 minus lambda, 0, 0. This is 2. So basically you will get negative lambda, 1 minus lambda, 1 minus lambda. Okay, so from here you will get first lambda equals to 0, second lambda equals to 1, third lambda equals to 1. Again, we have repeating eigenvalues 1. Okay, these are of the multiplicity 2. Now, if you have a repeating eigenvalue, and then the question asks you to check whether it is diagonalizable or not, the moment we have a repeating eigenvalue, so normally we will find the eigenvector for the repeating eigenvalue first. Don't find the eigenvector for this eigenvalue. Don't do that first. I will explain why later. Okay. So if you substitute lambda equals to 1 into our homogeneous system, okay, if you solve this, you will get this. So basically, from here, from the row 2 here, you will get x3 equals to 0. And then from the first row, you will get x1 equals to 0. Okay. So x2 we do not know. So then we put it as R. So the solution will be in this form, where R is any real number. Okay. So if you look at the general solution for the eigenvector here, it will be of the multiple 0, 1, 0. So meaning we cannot find two linearly independent eigenvectors for lambda equals to 1. Okay. So the moment you see that you cannot find two linearly independent eigenvectors, then we straight away make conclusion that A cannot be diagonalizable. So you do not need to find the eigenvectors for lambda equals to 0. So that's why normally we will find the eigenvector for the repeating eigenvalue first. Okay, so don't do this first, otherwise you waste your time if A is not diagonalizable. Okay, any question so far? Oleh? Okay. So you will understand more when you do your tutorials later on. Okay. And this is a hot question for midterm, something like this. So make sure you understand this. Otherwise, midterm you don't know how to do. Now the last example, okay, given eigenvalues lambda 1 equals to -1, lambda 2 equals to -2, lambda 3 equals to -1, and their respective eigenvectors, find matrix A. Okay. Remember from our page here, A, to find A, you can use this formula. A equals to P times D times P inverse. Okay. Now this is actually from here. So how do we get this from here to here? You understand, right? So make sure you know how to get this. The order of P and P inverse is important. The moment you get it wrong, then the formula is all wrong. Now, from here, meaning you need to find matrix P, you need to find D, you need to find P inverse. So that's what we are going to do. Okay. Let me see. So the first is we find P. So P is you just collect all the eigenvectors. Okay, so 0, 1, 1, 1, 1, 0, 1, 0, 0. Then from here you can get where D straight away. Is according to the order here, so this is the order. So this is lambda 1, lambda, this is x1, sorry, x1, x2, x3. So the order here is lambda 1, lambda 2, lambda 3. So for D is -1, -2, -1. So this is our D. So once you have P and D, you need to find the P inverse. Now from chapter 3, P inverse, you need to find two things. One is determinant of P, and then you need to find the adjoint. Okay, so the determinant is using this cofactor expansion. Okay, you will get P equals to -1. Or you no need to use cofactor expansion also can. Remember, I just recall we have a property here. Okay. Okay, never mind. You go back. Have a look. Have a try for the determinant. Okay, and then this is a matrix P for matrix P. Okay, we cannot use that property. Then once you know the determinant, you need to find the adjoint. Okay, so this is in chapter 3, you learned already. So let students solve the cofactors. Okay, so you will get the adjoint P equals to this. So the inverse is this. You will get something like this. So this is the inverse. So after that, you need to multiply all these three matrices together. 1, 2, 3 using this formula. Okay, then you will get this. So this is the matrix A. So this is another type of question that might come out in exam later on. Okay, I think that's it for today. If you have any question, then you just ask, I will answer. And that's it. So I'll stop the recording first. So basically, this chapter is, I think it's totally new to you. Okay. So this is the final chapter for the linear algebra part. So your midterm test will be chapter 1, chapter 2, chapter 3, chapter 4. And then this is the last chapter I will be with you together. So next week you will go to the statistic part. So the first few chapters, so starting next week, will be covered by Dr. Izzatu. Okay, Dr. Izzatu for, I think, for 3 chapters or 4 chapters.
So next week you already changed us. No,
You changed what?
we changed lecturer next week already.
Yeah. I will not be teaching you for the statistic part. For the math lecture, statistic part will be taught by Dr. Izzatu, our course coordinator. And then for my group, IS and MC, remember next week we have a quiz in Elite online. Okay, make sure you got it. And then I'll stop sharing the notes first. Reshare the QR again for those who haven't scanned. And then thank you for bearing with me for 4 weeks. Thank you and stay safe. Hopefully we can meet next semester. So, and that's it. Bye bye. Good luck for your midterm.
Bye, sir.
Thank you, sir.
Thank you, Doctor.
Thank you, sir.
Sir, sorry to interrupt, sir. You still there,
Yeah.
sir?
Yeah.
Louis asked in the chat, for the assignment, can we use handwritten? Because question 3, we need, according to his point of view, we need to use a mathematical software.
Yes, you can use handwritten one. No need to type. I know you are not familiar with typing max formula. So what you do is you just write and then you scan. You use cam scanner.
All right.
Okay.
Thank you, sir, for teaching us.
Okay.
Thank you, sir.
Yes, Nelson, the quiz is chapter 1 to 3. But for midterm is chapter 1, 2, 3, 4. Nelson, okay?